We now continue our look at these transformations, and in fact, I've included the word linear in the title of now two videos, but we've not really talked about what it means for a transformation to be linear. So that's going to be our focus in this video. What exactly do we mean by a linear transformation? Be able to identify them, and then look at some of their key properties, right? Let's define what a linear transformation is. So let T be a transformation from Rn to Rm, right? And again, so now we know what this notation is saying. T is a linear transformation if, that is, so if for every u and v in Rn and C in R, right? So for every pair of vectors in our domain and every scalar, every real constant, we have these two things. The first property that a linear transformation has to have is this. If you take the image of the sum of two vectors, let me put my little harpoon here to emphasize that these are vectors. So if I take the image of u plus v, I will always get the same result as taking the image of u and then adding the image of v. Right? So this is what we call like the additive property. So if your transformation is linear, it doesn't matter if you add two vectors first and then find the image of the sum, or you find the image of the vectors separately and then find the sum of the images, right? So in some situations, we say that the transformation preserves vector addition, meaning it doesn't matter if you add before or after you apply the transformation. The result will always be the same, right? So that's the property that relates to vector addition. And we've seen vector addition is a basic but yet a very important algebraic operation. The second requirement for a linear transformation, and thankfully there are only two, is this. If you take the transform, if you transform a scalar multiple of a vector, it's the same as taking the same scalar and multiplying the image of that vector. So in some sense, it almost gives you the power, right? It almost gives you the power to factor that constant outside of the transformation, right? Or think of it this way. If you find the image of a scaled vector, then that will always be equal to the scaled version, or I should say the scaled version of the image of that vector, right? So it doesn't matter if you scale the vector first and then apply the transformation, or apply the transformation first and then your scalar multiple. The result will always be the same, again, assuming that you have a linear transformation, right? So these two properties are very basic, but they're very useful in terms of identifying which transformations are linear and which ones aren't, right? So obviously the fact that this video is entitled Linear Transformations, this will be our focus, but we want to be able to identify when transformations might not be linear. All right, so let's take a look at a couple examples of this. All right, so our examples, we're going to determine which of the following transformations is linear or not, right? So we'll just ask this question. So is each transformation linear? And then of course justify. All right, so let's define a couple transformations and we'll apply this rule, right? So let's say the first one is from R3 to R3, right? So it takes a three-dimensional vector and it produces another three-dimensional vector, right? So what does it do? What are the actual operations? Well, here I'm going to show you that I'm going to write my vector now as a row, or actually an ordered triple. Let me write it as an ordered triple and say x, y, z. Now remember, there are different ways we can write our vectors, right? So this is a completely valid way of doing it. And then what does my transformation do to this vector? Well, let's say it produces the vector x squared, and then x plus y, and then y times z, right? So that's what my transformation does. It squares the x component, right, and keeps it in the x component. It adds the x and y components, and that's now my y component, and then it multiplies the y and z component, and it makes that my z component, right? So let's see if the first property is satisfied, right? So basically, because this definition is for all vectors in our domain, in this case R3, then we'd have to take two general vectors in R3 and perform this operation, right? And then perform these operations and see if we get the same result, right? If we get the same result for every pair of vectors in R3, right, then it would pass this test. Then we would have to check the scalar multiple test as well, right? So let's start with the additive requirement. So I'm going to let x1, y1, z1, and then x2, y2, z2. So these are my vectors. You can call them u and v if you'd like, but I have to keep them general. So these are my vectors in R3. All right. So let's do the operation on the on the left hand side and see what we get, right? So first I have to add them together. So in fact, yeah, let me call this one u and then this one v. So u plus v, well, we know how to add those two vectors together. We take x1 plus x2 and then y1 plus y2 and then z1 plus z2. So that's our basic vector addition. Now let's apply the transformation to this sum and see what we get. Right? So t of u plus v. Well, look at what it says. It says I have to take the x component and square it. So that means I have to square this, right? So I'm going to write this as, I'm just going to write it as the quantity squared. I'm not really going to FOIL anything out, but that's this, right? And then what does it do for the middle component? It takes the x and it adds it to the y. So it's going to take x1 plus x2 and add y1 plus y2. So x1 plus x2 plus y1 plus y2. All right. And then what does it do for the third component? Well, it takes the second component and multiplies the third component, and it makes that the third component of my image. So y1 plus y2 times z1 plus z2. So that's the expression of what I would get if I add two arbitrary vectors in R3 first and then apply the transformation. Now let's write down what would happen if we transform them separately. So if I find t of u and then t of v and then add them together. Well, let's see. And that I could probably do on one line. Let's see if we can pull that off. So t of u plus t of v. So there, I again remember what it does. It squares the first component, so I'll have x1 squared, and then it adds the x and the y component, so then this would be x1 plus y1. Oh, this is supposed to be a comma. Separate my components. And then it multiplies the second and third components to get the third component of the image. So y1, z1. Alright? And then add to that, and then it's basically the same pattern, but then with the 2's as my subscript. So I can basically look at this and write down what it will be like if I transform v separately. So I'll have x2 squared, x2 plus y2, keep putting a plus sign there, that's a comma, and then y2 times z2. So now let's add them together. Well, if we add them together, look at what happens. So I now have to take x1 squared plus x2 squared, and then I have to take x1 plus y1 and then plus x2 plus y2. And then finally, I have to take y1, z1 and add it to y2, z2. And then what I have to do, I have to compare the components of this image with the sum of these images and to see if they're the same. So here is what I get in the first component if I add first and then I transform. Right? That's what I get. If I transform first and then add, this is what I get. That's not the same. Right? So that's a problem. The middle components are the same, right? Because our addition is commutative, so these are the same. But then again, if I look at what happens in the third component, yeah, this, if I FOIL it out, will not be y1 z1 plus y2 z2. I will have additional terms here that are not here, right? So this compared with this, yeah. So the only components that are always the same would be the middle components. So since t of u plus v is not always equal to t of u plus t of v, then this transformation is not linear, right? So since t of u plus v is not equal to t of u plus t of v for all u and v in R3, t is not a linear transformation. It is some kind of transformation. In fact, it's a non-linear transformation. So t is not linear, right? So I don't even have to check the scalar product, right? Now, if this one had passed this test, then I would have to check to see what happens if I scale, say, u first and then transform it, and then or transform and then multiply by the scalar, right? Then I would have to check that. But since it doesn't pass the additive property, then I don't even have to check the second one. All right. Now, now let me just kind of go back and look at this to see if there is something we could have picked up on earlier. Here, if you think in terms of an x squared, remember going all the way back to when we defined a linear equation, that we couldn't have our variable raised to a power that's different from 1. So that's a problem right there. We also had the requirement that we couldn't have the product of two variables, right? So these two were kind of red flags. Notice we are allowed to add two variables, and notice that that didn't affect, like the middle components worked out nicely, right? But not the first and the third, because these, just thinking back to how we defined a linear equation back pretty much on day 1, right? We're not allowed to have expressions like this, and we're certainly not allowed to have expressions like this. So those are some clues that you can look at to see, okay, is this thing really going to have these required properties or not? All right, so let's look at a second example. So let's look at example 2. And for this one, I am going to take a transformation that goes from R4 and gives me a vector in R2, right? And again, I'll follow this pattern here, and I'll write my vectors now as ordered. So I'll start with an ordered quadruple, and then write down the ordered pair, right? Because we're going from R4, which is 4-dimensional, to R2, which is 2-dimensional. And here is our rule. So I'll say T x1, x2, x3, and x4, right? So here's my general vector in R4, just written as an ordered quadruple. And this is what my transformation does. It's going to create a vector in R2 by doing this. It's going to take 2x1 and then add x2, and then it's going to take x3 and then minus 3x4, right? So this is the operation that my transformation does. It's clearly well defined. Any vector in R4 that I start with, I can always perform these operations. And let's see if this transformation is in fact linear, right? So I'm going to say let u. So I'm going to use this as my first one. So I'm just going to take u as my vector x1, x2, x3, x4, and then I'm going to take v to be, I'll just change those x's to y's, right? So I'll just say y1, y2, y3, y4, with the understanding that each x and each y, those are constants, right? So we have numbers in our components, all right? So let's go through and see if we can verify each of these properties. So first I am going to add these two together. So u plus v is the sum x1 plus y1, comma, x2 plus y2, comma, x3 plus y3, comma, and then x4 plus y4. Okay, let's take the transform of the sum. So if I try to find the image of the sum of these two vectors, u plus v, well, look at what it says. It says take your first component, double it. So I need to double this. So 2x1 plus y1, and then add the second component. So add this. So plus x2 plus y2, comma, and then it says take the third component, which is my x3 plus y3, and then minus 3 times the fourth component. So minus 3 times x4 plus y4. Right? Now, I could do the t of u and then t of v separately and compare it to this, or this is look at what I could do. I could actually kind of collect these terms. So I'm going to collect all the terms that have the x's. So I'm going to do it this way. So I have a 2x1 and then a plus x2. So I'm going to group those. And then I'm going to group the y's. So then I'll have plus, and then I'll have 2y1 plus y2. Right? And I can do that because of the addition, and I can move stuff around. Similarly here, group the x's. So I have x3 minus 3x4, and then plus, and then I have a y3 minus 3y4. But because this is a vector, and because of my vector algebra, I can write this big vector as, so now I'm going to separate the x's in their own special vector. So in other words, I'm going to take this and put it in the first component here. So 2x1, x2, and then comma, and then again take the x3 minus 3x4 and put that here. So x3 minus 3x4, and then add to that, because look, there is the addition. So add to that this separate vector now that contains the y terms. So 2y1 plus y2, and then comma, and then y3 minus 3y4. Now how does that help? Well, look at this. This is exactly t of u. So right here, this is t of u. This is what I get when I transform my u vector. And similarly, this is exactly what I get when I transform my y vector. So it's plus, or v vector. So then this is t of v. So this shows the connection that by taking the image of the sum and using my vector algebra, I can show that the image of the sum is the sum of the images, right? So therefore, our first property holds. Now we have to check the scalar one, and that one's a little bit easier. So what I'm going to do is I'm going to start with, I'm going to take my vector u and multiply it by any scalar. So for c in the set of real numbers, c times u is the vector cx1, cx2, cx3, cx4. So now let's transform this scaled vector and see what happens. So therefore, t of cu, so remember how we transform it? So this says we double the first component, so 2cx1, and then add the second component, so plus cx2, and then take the third component, cx3, and then do minus 3 times the fourth component. I forgot my comma there. So then minus 3cx4. But the interesting thing now is the c is a common factor in every term. So both terms in the first component, both terms in the second component. So again, using my basic vector algebra, I can factor out the c. So I can put my c outside, and then what am I left with? 2x1 plus x2, comma, x3 minus 3x4. And again, this is the vector t of u. So this is the image of u. So this is equal to c times t of u. And this works for every pair of vectors and every scalar, right? So none of the properties here depend on, me choosing a specific value for x1, x2, x3, x4, or y1, y2, y3, y4, or me choosing a specific scalar. It works for any constant and for any pair of vectors. So because of this, this transformation is linear, right? So therefore, T is a linear transformation. All right? Good. So again, it might not be the most efficient way, but that's the way we prove it, because it's based solely on the definition. All right. So now let's take a look at this transformation T. Right. So if we take a look at this. So this is a transformation that takes a four-dimensional vector and it produces a two-dimensional vector, right? So I wonder if we could represent this transformation in the form of a like matrix, right? So could we find a matrix that would transform the vector x1, x2, x3, x4 and produce this vector 2x1 plus x2 comma x3 minus 3x4. So let's see how to do this. Okay, so let me do this. I am going to copy this down. Right, so we're going to copy that. That way we have enough room to do what we're going to do here. I'm just going to paste it down here. And there we go. All right, so here's our transformation. So the question is now, is there a way I can represent this transformation using our matrix algebra? So to do that, I am going to write my vector as a column now. So this is what I'm going to do. I'm going to write it as a column. Right. And then so this is my so this would be my 4x1 column. And what I would like to be able to do is to find a matrix that when I multiply this column, it will give me this other column over here. And what I want now is this vector in R2 to be represented as a column. So I'm going to write this as 2x1 plus x2, and then I want my second component here to be x3 minus 3x4. So think about what it is I want. I want to find a matrix that when I multiply this particular column, I will get this column, right, which is a 2x1, right? Well, let's think about it. In order for this product to work, right, my matrix will have to have 4 columns, right? So it will have to be something by 4. But then if I want the answer to be a 2x1, so then this matrix will have to be a 2x4, right? So we need a 2x4 times this 4x1 to give me a 2x1. But think about it. So I need to have 2 rows, right? Well, what are the entries in those rows? Well, let's think about it. I want to double the value x1. So I would have to have a 2 there, right? And then I want to add 1 times x2. So I'd have to put a 1 there. And then I'm not including x3, so there's like a 0x3 and the 0x4. So I would need to put zeros there. Because if I did that and then did my row times the column, I would have 2 times x1 plus 1 times x2 plus 0 times x3 plus 0 times x4. And that's exactly what I have here in my first row, first column, or only column, right? And then think about it. So now, what would I need? What numbers would have to be in the second row of my matrix? Well, there is no x1, so I'd have to have a 0 there. There is no x2, so I'd have to have a 0 there. There is a 1x3, so I'd need to put a 1 in that position. And then there's a minus 3x4, so I'd have to put a minus 3 in that position. Then now, if I took this row and again multiplied my column from R4, I'd just have to make sure, I just have to verify that I get this expression, which is what the transformation says I should get. Well, let's see. I'd have 0 times x1 plus 0 times x2 plus 1 times x3 minus 3 times x4. And that's exactly what my transformation does. So I can think of the transformation kind of as this formula, but now I can actually reinterpret my transformation in the form of matrix multiplication. I just have to make sure that all my dimensions match up. So here is the column that represents my input. Since it's a 4 by 1, right? We know we're starting from R4. Here is the column that represents my output. I'm generating 2-dimensional vectors in R2. And in order for me to use a matrix multiplication, I have to use my definition of matrix, the product of two matrices, to figure out what my dimension is. And this is kind of interesting because I'm going from R4 to R2, but my matrix is a 2 by 4. It's like they get switched, right? And that's because I need to have the same number of columns here as rows here. So the rows are stated first here, but then the columns are stated second over here. So this particular matrix, right, is referred to as the standard matrix of this linear transformation. So let's call it A, right? So A is called the standard matrix right? It's the standard matrix of the linear transformation, right? And it turns out, and I'll state this as a theorem, and it's not difficult to prove, but we're getting close to the end of this video. I just want to wrap up kind of, and I think the theorem will be a very good summary. And it basically says this: every linear transformation from Rn to Rm can be expressed as a matrix transformation, or using matrix multiplication with the appropriate sized matrix, right? So every linear transformation can be written in this particular form, and therefore will have they will each have its own standard matrix, right? So every linear transformation from, in fact, let me write it like this. Let's use our nice function notation. So every linear transformation that goes from Rn to Rm can be expressed in the form, right? So what I'll do is I'll just say there's going to be some coefficient matrix, and then I'll have a vector u, and then there will be, this will be my vector v. So expressed in this form, where A is, and then it would be an M by N matrix. So A is an M by N matrix, right? Known as the standard matrix of T. So known as the standard matrix of T, right? And this is really powerful. Why is this powerful? Because we have a lot of knowledge about matrices now. So the fact that every linear transformation can be represented in this matrix form, now it gives us a way to do a lot of things. I mean, we know about matrix multiplication, we know about determinants and inverses, so maybe those things can also be applied to linear transformations and can shed more light on their properties and so forth. So I don't know, I'm looking forward to the next few videos. Hopefully you're excited as I am, because I mean, it's like we're just opening this whole new world, but yet we're seeing familiar friends, or maybe foes, but I don't know. They're all friends to me. So I'll see you in the next video.